I'm Brian Jelinski-Smith, and I'm one of the product managers working within HBK, primarily within the vibration test systems environment. And first, I'd like to just take you kind of through a bit about us and also a bit about kind of who we are and the vibration test system element before Kurt, my co-presenter, will talk you through a bit more along the Princia side and the what that can do and how that can be linked into vibration testing and that specific area as well. So if we just move on. So HBK. So HBK is a new organization formed from two specific companies, Hottinger Baudimischertechnik, who are based out of Darmstadt in Germany, and Brüning Care, who are based in Neum in Denmark. Those two companies, very, very similar, both very, very dominant within the test and measurement chain, and so they came together and formed HBK. Now, HBK themselves, we have a great value offering. That value offering is things like, an integrated test and measurement platform. So across HBK, we have a plentiful array of different products within the portfolio, specifically devoted to, as I said, this test and measurement chain, whether it be measuring sound, measuring vibration, understanding that, acquiring data, doing that analysis, both pre and post, and really kind of honing in on this particular kind of area. It gives us and our customers and the market insight and confidence in not only product creation, but product validation, and product continuation and improvement as well. So it's all part of that fundamental process from birth, even before birth as well, all the way through that conceptual stages, all the way through to product launch, all the way through product launch, through its product life, and also out the other side as well, on both the OEM side and also on customer side. So really kind of getting to grips with that. We ourselves, HBK, we consider ourselves as being the product physics expert in the field. And that is because of the plethora of knowledge that we have and products in our portfolio to help our customers and you guys deliver insights and improve your products and improve your testing using all the many tools that we have. We are aligned both physically and digitally to your needs and also to the market, whether it be through physical testing on what I'm going to talk about, which is our shaker systems, or in the digital domain, looking at more the encode ReliSoft side, which is along the Princia element of things. And ultimately, we are driving kind of real data. So we are looking at acquiring that data, developing with that data, using that data, and making better products and better decisions based on that data. As they say, data is key. So moving on, I'll talk roughly about kind of the two elements of it. So my side, which is the left-hand side of the screen at the moment, which is the LDS side. So LDS is the product range supplied by Brüning Care, which is part of HBK. And LDS is the, like I said, brand name for the shaker systems. Now, shaker systems come in many different flavors and sizes, from the size of a teacup, for those in kind of English and tea drinking societies, all the way up to massive systems for testing full satellites, rockets, full car assemblies, and upwards. So we've got a real kind of size gauge to contend with. The LDS standards had gone through many different rebirths through different ownerships, but ultimately we've been around since about the 1960s, and originally came from kind of amplifier development, and from there we've gone through strength upon strength, actually looking more into the vibration analysis and physical testing areas within the market. The range itself, which I'll come into in a bit, but more focusing on applications, does go from about 2 newtons, which is this teacup size, all the way up to just shy of 300 kilonewtons. So again, it's a real depth and breadth type scenario where we've got shakers going from the smallest up to the biggest, and amplifiers to suit, along with many other products that fit within that realm. On the Princia side, which Kurt will go into a bit more. They've got some really, really great kind of products in there. Those products, which you can see on there with regards to those brands, you've got the Encode in there, you've got Reliasoft. They do a lot of training. They've got a really good training kind of environment and platform that they work on, and they've got a really good services department as well, both of which kind of are really strengthening the entire HBK platform with that. Princier and the LDS brand names, obviously both part of HBK, and both of them together are bringing this virtual and physical kind of testing realms together. So by doing that, we're able to simulate and predict product fatigue life. So from the Princier side, you can do that by doing a lot of work up front to guide product development and to validate prior to physical testing on shakers. This allows for a lot of design work to be done up front, a lot of validation to be done up front, a lot of understanding to be done up front, and also ultimately remove a lot of cost from that entire development cycle. It also gives validation on product reliability. So when you're running a test, this allows you to run that test all the way through to failure. So what you can do is you can then help with life prediction and to understand kind of fail pass margins, kind of what it's going to take to get it to a pass, what it's going to take to get to a fail. And you can do, again, a lot of that upfront prior to the physical side of it. And then you can validate what you've done theoretically through the digital realm, the physical shaker. And ultimately, you know, this is all about expediting the product iteration cycle, the product development cycle, and obviously looking at the reduction in the cost to you as product developers and service developers to get a product to market, and a successful one as well. So a vibration test system. If we talk about the physical realm really is, again, it's a real depth and breadth. Again, as I said, you've got really, really small systems which can incite really high frequencies but low force, really good for high frequency testing of small components, semiconductors, modal and structural analysis, that kind of element of things, all the way up to the big side. So you're looking at full assemblies, full big, you know, consumer goods, rockets, cars, you name it. And again, validating the design work that has been done prior to that stage. So every single system that we start with, you always start in one place, and that, of course, is the device and the test. You know, you've got your component, you've got your product, you've got the thing that you've been working on that needs to be validated. To validate that, you know, you need to have a system that is capable of testing its physical mass, testing it to the levels that you want to test it to. So once you know what that is, once you know kind of what profiles, what standards you need to test to, and again, a lot of this you can do up front, and you will be able to do it up front within that digital twin element that the Princier range can offer. After that, you then have the vibrator, so the big lump of metal that moves up and down, that shakes this component. And that can come in, again, different flavors, whether it be permanent magnet or electromagnet. They can shift lots of different forces. They can support many different masses. But ultimately, this vibrator is designed to simulate the vibration that is that vibration profile that needs to be incited into that component and that product. After that, we then have the amplifier. Now, the amplifier is obviously doing that, amplifying that signal that is being generated. And that signal is coming from what we call the controller. So this controller is basically the input side of things. So you design your profile within it, or you import that from another device. Quite often you can take the output from a lot of the digital side of things. So once you've done your analysis and you know what profile you're going to need to do, you can take that, you can output that as a PSD, and you can import that directly into the vibration controller. From there, you can send that through to the amplifier, which then amplifies that that signal and sends that drive signal through to the vibrator. And all the time there is this control loop going on. So this control loop is then kind of completed by what we call the accelerometers. So these accelerometers, again, they come in many different shapes and sizes and, are designed for many different types of purposes. But ultimately what we're doing is we always place one on the table, whether that be in the vertical or horizontal. So looking at developing at monitoring that so that we know what input is going into that component, and then going from there on to kind of monitoring what is happening on that component. So feeding that back into your controller to make sure that you're not going above any limits that have been set. Because ultimately, if you spend a lot of money developing something and all you're looking at doing is validating it, you don't necessarily want to take it all the way through to a destruction level. You can do that digitally, but you may not want to do that physically. Again, that's up to your test regime. But that is kind of where we stand with an overall vibration test system. And these systems are used throughout the world in many, many different scenarios, many different industries and applications. So I've talked a little bit about the products and the actual setup of a vibration test system. But that's the product side. We're not looking at the solution side. What solution does that give you? What can you do with these systems? So these systems kind of, again, can serve many, many, many different markets. And each one of those markets has a tendency to lean towards a type of shaker and others tend to lean to another. So if we just look at the range that we offer as a reference, so I refer to the V100 and the V455 as being permanent magnet shakers, but ultimately they're low force, high frequency shakers. And within that realm, you then start looking at things like subcomponent testing, looking at semiconductor testing, educational research, structural analysis, modal testing. You start kind of going into that, even inciting anti-phase frequencies into automotive vehicles or systems that have a high susceptibility to vibration. So you can then, you're looking at replicating high frequencies typically, but low force and low mass. So these tend to be connected indirectly to other systems. Like I said, typically they go with telecom audio, so looking at testing of phones, your mobile phones. We've all dropped them. And what you can do is you can then simulate those drops, simulate them in transit. And also, like I said, with educational side, you can do a lot of structural testing with that as well. When we start moving up into the low force realm, so from our product range, that looks like the V555 up to the V780, and this is our we start going forward into the kilonewton stage, so out of the newtons into the kilonewtons. Again, relatively low force, low mass yield with regards to how much mass they can actually hold within the shaker. But what they do is the frequency is coming down slightly because we're imparting more displacement and also more force. So that then shifts the markets that they're in and also the type of applications that they can get used in. So what we start doing is replicating kind of road noise and road data. So simulating those types of environments. You can get a four-poster set up, have a car slung over four shakers, and what we can do is we can independently or in unison incite a vibration into a car to understand kind of how it reacts from a suspension side, and also how the componentry within it kind of reacts. Also, we're looking at aerospace and defense. So again, putting those vibrations in through a structure to understand if the electronics and componentry can cope with what's happening through that data that has been acquired through flight or through the various situations that we see in aerospace and defense, such as a missile launch or anything like that. And again, telecom audio again appears because, again, what you're doing is you're looking at how people use devices. Devices see a lot of wear and tear on a day-to-day basis, either through transport, through being dropped, through being in a bag, through being in a purse, slung on a table. And all the time they're seeing these impacts and seeing these various different use case scenarios. And with that, obviously you want to replicate it. So again, you can do all of this. Once you've done your validation, you can then simulate that physically in this physical and real world environment on a shaker. Then we head over into our medium force area. So medium force is for us is the V830 to the V8, but now we're going from kind of tens of kilonewtons up to around about 50, between 50 and 60 kilonewtons. So a lot more force, and with that, these systems become a lot bigger. So we go from being about the size of a football, which are the kind of low force shakers, up to these medium force shakers, which are the size of probably like your patio set that you would have, or an umbrella or a motorbike type physical size, just for reference. And one of the things that you'll see is the type of applications that I use within this have now started to shift. So we're going away from educational sides. We're going away from kind of desktop applications, primarily because of size and weight, but also for what they can do. By these being much larger, it opens the door a lot to being able to test high, much bigger applications with higher forces that need to be imparted into them. Shock profiles. We can start looking at very different profiles such as sign and random, different sign profiles as well, more aggressive type scenarios, because you've got more capability with these systems, and these systems are also electrodynamic. So within that, there needs to be a lot more cooling, which again allows for greater force to be imparted. Now here we're starting to see the move into the automotive and aerospace, even more so than before. So now we're into the point where we're testing things like dashboards for general durability testing, but also we're doing testing such as squeak and rattle, so understanding how much noise something makes. You're also testing kind of long pointy things such as missiles, things like that. Again, these are all situated on these shakers, and that allows you to simulate, again, kind of shock response spectrum type profiles, high shock scenarios for cars, for impacts, those kind of things, and you can do all of that within these types of shakers. So again, these are quite big now, and they have a larger scope with regards to what they can test. And the other benefit of these things is you can mount directly onto the armature themselves. So you're no longer indirectly mounting through stingers or just having it supported elsewhere and then just applying the vibration. What you can now do is you can import that directly into that product, and you can mount directly onto the top, fix it so that it's just one solid object, and move that. And that gives a lot more flexibility with what you're doing. You can then start testing arrays, and also you can connect it with a combo system. Now, a combo system is basically the way that you would go from testing in the vertical, which is what you're seeing in front of you on these shakers, where everything's testing in the single axis going up and down, and you can rotate that by 90 degrees and then fix that and connect everything to what we call a slip table, which is basically a big magnesium plate to allow you to test in longitudinal and latitudinal directions. By doing that, you can then address all three axes. So you can test in your vertical and your horizontal twice over. So you can test in all three axes to validate whatever product you've got and for whatever reasons that you've got them. Because in the real world environment, you don't just see one type of vibration, which is, because you're only ever moving in one constant direction, in one constant path. Even walking, if you're walking forward, you've got different motions constantly happening, because you never walk completely true. So you're moving from side to side. You've got the impacts, because every time you hit the ground, it's kind of pushing back onto you. So you're getting kind of shock coming vertically back up through your body. So all of these different things, to see a real world environment, you're seeing it from all three angles, and that's what needs to be replicated and tested. And that's the good thing about having it with a combination and a combo SIP table, is you can do that. High force being the V8900 to the 994. It ranges from around about 80 kilonewtons up to just shy of 300 kilonewtons. These are the big boys. These things are designed to test full assembly, so full cars, satellites, rockets, and imparting high forces to replicate these real impacts or these real kind of replicating much more of the more extreme environments that you would see. So again, your crash testing, your launches, your high G environments, your high acceleration, your also when you come into a stop, so you're looking at your velocities, all of this, we can now replicate. And that's the core thing. It's all about replication of what we're seeing in the real world, but putting that through a physical product in a physical environment. So just to quickly recap, everything that you've seen prior, each one of those shakers and across the board, whether it's with us or anybody else, they validate and test for durability and test for endurance and allow you to fully launch a product that is going to work in a real world environment for any market that you can possibly think of. Anything that is in front of you now at your desks has most definitely been tested in some shape or form, directly or indirectly, with either a digital or physical vibration test. Even the pens that you're working on, they would have been tested against package testing to make sure that they don't blow up en route to the stationery store and they don't leak everywhere. So that packaging would have been package tested on a shaker. It would have also been designed in a digital environment and probably even tested originally and validated in a digital environment. So again, everything is vibration tested and simulated in one form or another. And that is that's the whole reason behind what we're doing, and the whole reason why you're here as well, to understand that and to understand the benefits that it can give us. And like I said, that is a real core thing, and it's all about taking it from prototype through test and through validation stages. So where does that leave us? Well, again, this is the test and measurement chain. So the test and measurement chain, as I mentioned before, is part of HBK. It allows us to offer full value offering to our customers and allows you guys access to, again, the entire value offering and for your test and measurement chain and your validation of your designs and prototypes. So to understand where you're going, you've always got to know what component it is or assembly you want to test. Understand that's the first stepping stone, and that allows you to then progress either digitally, physically, or through both elements of your vibration test and validation scenario. Once you know that, then then you can work out the type of vibration that you want to simulate and how you want to simulate it, what standards you need to do, whether you need to create your own standards, whether you need to create your own profiles, whether you want to kind of amalgamate a military standard with your own product standard or a customer's product standard, and how you want to kind of do that to better your product and to better validate it. You then need to work out what data you need to capture and how you're going to capture it, what you want to do with that data that you're capturing. And then ultimately, as I said, what information you want to acquire from that data. What are you trying to get out of it? Is it to validate the product? Is it to better design that product? Is it to create an award-winning product that means that you don't have to have your music on really loud in your car because your car is now completely silent on the inside? It's all of these things that you need to kind of work out and define, and that'll allow you to define whether you're going to go down the physical route, the digital route, or, which is one of the greatest scenarios, doing it in tandem and having them both. So having the physical and the digital twin. So at this point, I would like to hand over to my colleague, Kurt, who can then take you through his side and the Princia side and talk a bit more about the digital twin element of the vibration test and measurement chain world. So Kurt, over to you.
Great. Thank you, Brian. Hi, everybody. My name is Kurt Munson, and let me just regain control here of my screen. Let's make sure. Here we go. All right. So, Brian, thanks for the introduction. Great overview there of these shaker rigs and various applications thereof. My name is Kurt Munson, and I'm the application engineering manager at Prencia. And what I want to do now is go one step past the shaker and think about how do we really optimally use it? And really, if we're looking at validating the durability or endurance or reliability of a product that we're engineering, I want to give you 3 challenges today, 3 ways that we can improve these shaker tests, okay? So just first is, how do we design intelligently the shaker profile? So, for example, if this exhaust system that we see here, if it sees vibration from the engine in the road and so on, how do we replicate that on the test rig? For example, we might do PSD random testing for X number of hours at Y frequency band and Z amplitudes. The question is, though, number one, what amplitudes, what frequencies, and for how long? We can learn how to do this from measured vibration data, and we can even make comparisons of vibration measurement and its fatigue potential relative to standards from, say, MIL standards 810 or DO 160 or SAE standards. So designing an intelligent vibration profile can be a really attractive proposition here, because ultimately we want to make sure that the shaker rig is producing vibration that's representative of the actual service environment that the product on test will be in. We don't want to test in a way that's not realistic. We want to make sure that our test spectrum, our vibration profile, is realistically designed. And we'll have more detail on this later in this presentation. Secondly, we want to introduce the concept of numerical simulation in the digital twin. So we want to make a digital model, say a finite element model, of the device on test, because we can use this to do things like validate that the vibration testing we're doing makes sense. And also we can look at what potential failure mode should we be looking for during durability testing. And even better, we can run a virtual shaker table test through using some ENCODE software to look at virtually predicting fatigue life and then gaining confidence virtually in our part such that we don't get stuck in this, let's build it and let's test it and oops, it breaks. So let's rebuild it and retest it, and oops, it breaks again. We want to gain confidence in the robustness of our design virtually before we take the time and money to put this part on test. Okay, so we'll have more detail on this digital twin numeric simulation concept in just a minute as well. Third challenge for today is, let's see what we can learn by understanding product reliability. Rather than just testing a part and saying, oh, it passed. We have to understand the statistics of a population. It may be that your part is designed according to some reliability specification that says, say, we need to demonstrate that no more than 5% of these parts will fail after 10 years of service. So maybe there's a reliability specification. And if we run our tests right, we can not just run to pass or fail, but learn a lot more about failure modes and failure rates and ultimately reliability and design margins by going a little bit further and having some, not all, running some of these parts to failure. So I want to dig into these 3 things today. Intelligently designing the spec, the vibration profile, using the digital twin in the virtual world, and lastly, bringing reliability and design margins into play. All right, so let's dig into this. Now, think about this from the perspective of how do parts go from conception to becoming, say, that product on your desk, as Brian said. You know, in the beginning, parts are designed, so shape and material and so on. This part needs to be able to resist these vibration levels for X period of time and such. So here we have a conceived design. I think that this design meets functional intent. And then we build prototypes for testing. Now, the neat thing is that if we build a prototype, number one, we're going to need to test something at some point to the actual validation step. But number 2, we can use this prototype and the way it vibrates in our understanding, our measurements, for example, to gain confidence in its digital twin. So a really important thing here is that we can use this prototype as a correlation tool with its virtual digital twin. right? So gaining confidence in the CAA world, in the predictive world, is something that the prototype allows us to do. Now, with prototypes, then we have some qualification testing, validation testing. It might be PSD random, it might be sign-on random, it might be sign sweep, it might be shock testing, whatever it is. But we take this physical part and we subject it to some vibration levels that are representative of the actual environment it will be in. And we look and see, does it last long enough? How does it fail? Now, this might be a pass-fail test. It might be that we have a specification that says test it for the equivalent of X years. And if it passes, great. But my challenge to you guys today is we can actually go past that and start to think about design margins and think about product reliability. Because ultimately, we're not in the business of building a prototype and showing that it works. We're in the business of building, say, hundreds of parts or thousands or maybe even millions of phones and ensuring that the population meets its functional intent for its required time. So reliability comes into play. Ultimately, those parts, as I said, are going to be produced in tens, hundreds, thousands, or even millions, kind of a scale over time. And, the reliability side becomes important then because we need to think about what kind of warranty returns are we going to have, what failure rates and warranty costs do we look at? And then how do we optimize, say, a maintenance strategy? If it's a high value asset where there's a maintenance aspect to it, then we can optimize maintenance to improve reliability and reduce cost. So this is kind of like you can kind of look at it as the product development calendar from design through qualification through to service. And you'll see these three main points I'm trying to make today play in here in several different ways. So let's dig into those three main points, the three challenges of how we can have a better shaker test. So let's look at the vibration profile design. Okay, so here's one of these awesome shaker rigs, and it looks like it's got a radiator of some sort, some kind of a heat exchanger that is being subjected to vibration to ensure that it doesn't leak or break over time. A big question is, what's a representative test specification? So, for example, what frequencies, what magnitudes, and for how long? Those are the big questions. That's what we need to give to the shaker controller. A PSD, a sign sweep, a sign on random, a shock train, something like that. But the question is, say for PSD random, what frequencies, what magnitudes, and for how long? Now, you may be using a standard for this. For example, there are SAE standards that say batteries in a vehicle, batteries in a car, in a truck, something like that. See typical vibration levels like this. There are also military standards, DO 160 and Mil Standard 810G do this. Now, the challenge here is standards are nice, but we have to be careful in assessing how applicable they are. Because I'll be honest, some of these are older than me. Some of these vibration standards are older than I am. And the challenge that represents it then is that the standard may have been developed in a time when, say, batteries were something you bought at the store and threw away when you're done with them. As opposed to now, electrification is upon us. The world has changed a lot. We live in a connected, electrified, and just a different environment than we used to. And the challenge here is we need to recognize that standards, while useful, may not actually represent the vibration environment that our part sees these days, which is why then we would use vibration instrumentation like accelerometers and such and measure vibration versus time. That's what we see on the left side here, these time series. We can use that measured vibration data in service on a prototype to develop a test specification. For example, the PSD that you see at the bottom of the screen. ENCODE software, ENCODE GlyphWorks, has a great module in it that allows us to look at what frequencies, what magnitudes, and for how long should we test, given fatigue rules. So bringing durability rules like an SN curve and such into the calculations. We can also use ENCODE GlyphWorks software to compare test specifications. For example, maybe supplier A says, we're doing a PSD random test. And maybe supplier B says, we don't have that capability. We're going to do a swept sign test. Now, how do we know which test is more severe? Are those tests similar to each other? PSD random is very different excitation than sign sweep. There's nothing right or wrong with either of them. we can use ENCODE GlyphWorks to make comparisons between those two and look and see, are these tests being run by different suppliers really similar? Is there something fundamentally different about them in the way they produce fatigue damage in our part on test? We can also use ENCODE GlyphWorks software to reduce test time by increasing excitation levels. We often need to prove that our part is going to last a really, really long time, but prove it in a very short time. One way to do that is to accelerate these test profiles. So the GRMS level or the excitation levels can increase, which will reduce test time. Now, what's that relationship? Is that a linear relationship between GRMS and test time? I'll give you a hint. It's not. We need to take into account damage and fatigue failure modes in an SN curve and such. So ENCODE allows us to do this. We can look at how does increasing excitation levels increase the damage accumulation rate, and in turn reduce the required amount of test time. We can turn this around as well, though, and look at derating or adjusting down a shaker profile. Now you may ask, why would we do that? That's the opposite of accelerating a test. And the answer is we may need to do this at some point to use a shaker rig that we have in our lab. Maybe the test articles have gotten larger, and we're maybe kind of in a marginal range using an existing shaker. So what we can do then is dial back the excitation levels so we can use our existing test rig that we have. And in doing so, we can then say, let's run longer. But that relationship between excitation levels and how long to run, that's the really key part, is recognizing that there are fatigue rules should come into play in adjusting this profile up or down in its time dependence. Now, that's one challenge. So how do we create an intelligent vibration profile? ENCODE GlyphWorks has got us covered there. Let's talk about the digital twin concept. So let's do everything we can to simulate fatigue life and answer what-if questions. So first point, we want to virtually test our part. We want to predict fatigue life before we commit to building and testing prototypes. The old build it, test it, break it loop is very expensive and time consuming. So what we don't want to do is build a part and say, you know what, I think this is going to last on our test rig. I think this will meet the customer's vibration specification. Let's test it and see. What we want to do is gain confidence in the robustness, the durability, and vibration behavior of our part. And if we can do that digitally, that means we have a greater chance of passing our test and not falling into this build it, break it, fix it loop, which, as I said, is extremely expensive. So we can also use tools like ENCODE Design Life to predict fatigue life and understand design margins. So, for example, if we do have a physical part on test that passes the 12-hour test, that's great. Maybe we have a 12-hour test that's equivalent of an entire customer usage duty cycle. So to pass that test is great. But even better, wouldn't it be nice to know the design margin? To be able to predict the design margin, to say, you know, are we barely passing the test? Do we have a lot of overhead in terms of durable remaining life? If so, maybe we can cost reduce or reduce weight and understand how to optimize these designs based on durability specifications. And lastly, the digital twin allows us to investigate failure modes and avoid them next time. So if we do the FEA and the stress analysis and the vibration analysis up front, we can use the prototype as a correlation tool to understand our ability and to gain confidence in the digital twin's ability to provide predictions. If we do all that up front, the neat thing is now it's really easy for us to investigate what-if scenarios and investigate failure modes and so on. So that's my second challenge to you of the day, a smarter test by the use of a digital twin, the virtual shaker table, we could call this. Okay. Now, my third challenge to you guys is let's look at going from a pass-fail into a condition of understanding reliability or understanding design margins. So first off, we need to look at when we're designing that test. I spoke before of how we can design the shaker profile. We can look at what frequencies, we can assess what frequencies, we can assess what magnitudes of excitation and how long to run using ENCODE GlyphWorks software. I want to go one step past that, though, and look at this from a statistical perspective. And we're going to bring in this product we call ReliaSoft Weibull++ into play. We need to recognize that if we have one part pass, that doesn't tell us much about the population of 1 million phones that we may produce and ship to our customers. So looking at this statistically, we need to think about things like not just what's the shaker profile, but how long should we test and how many units should we test? So for example, if our specification says we need to demonstrate that our part is say 95% reliable with a certain confidence level, reliability like R95C90, some people talk about. We need to show that not just one part passes, but we need to demonstrate that of a population, the failure rate is going to be quantifiably low, that say only 5% of parts will fail after 1 year, for example. We can use statistics in reliability engineering and Weibull++ software to say, hey, look, we can test to one life according to this sign-on random profile, but we should test 10 parts or 12 parts or 20 parts to be able to demonstrate that the reliability and confidence requirements are indeed being met. Secondly, now this can get a little bit expensive, but we can learn so much. So I challenge you here to think past test, to think outside the box and shift your focus away from pass-fail testing to testing at least until some of these parts fail. So rather than saying one life is, say, 12 hours on the test rig, and if 12 hours pass and none of the parts have failed, we smile and nod and say, great, pat ourselves on the back, our parts passed. Let's continue to test. Let's continue to test until, not all, but we get some failures. We can learn some really great things in doing so. Number one, we can learn about failure modes. We can learn, are we really producing the failure modes that we expect? What are those failure modes? What are those weak points, right? One thing we don't want to do is have a test pass just because we're shaking it the wrong way, just because we're not exciting a certain failure mode. So failures we can learn a lot from. Don't be scared of these things. So we can learn about failure modes. Secondly, with even just a few failures, we can begin to look at the statistics of failure and calculate things like, what is the actual reliability? The specification may say we need to meet a reliability target of 95%. If we find out that at one life, our actual reliability is 99.9999%, that's great from a product perspective. We're not going to get a lot of warranty returns, but understanding that margin allows us to optimize reliability, optimize product design, because maybe we're overbuilding, maybe we're over-designing. Maybe it's too expensive. Maybe we have additional weight in this product that we shouldn't because it's been over-designed. So to calculate actual reliability is a huge benefit to us because then we can start to think about warranty, cost implications, and optimizing design for reliability. So my three things that I wanted to get across to you today, 3 ways to improve shaker tests. Let's just review these, and then we'll get to questions and answers. First off, I said we can use ENCODE software to design a vibration profile. Now, we can design a vibration profile based on measured vibration data. You may be using existing standard vibration profiles. We can use ENCODE software to compare those and look and see, is the vibration profile from the standard that we've always been using, have we always been over-testing or under-testing from a fatigue perspective? So designing an intelligent vibration profile is one really key enabler that ENCODE software brings to the table. We can also use the digital twin concept to perform numeric simulations. So we can look at this in a predictive way, rather than always relying on testing parts to break them and then improving design. Why don't we go around that design improvement loop digitally so that we are spending less time on building prototypes and we can focus more on design improvement in a digital world rather than always relying on doing so in a physical world. And lastly, we looked at ways to calculate product reliability, taking a step past the pass-fail concept, and even with a few product failures, even a couple product failures at extended times, if we continue to run that test, can give us a lot of information about actual product reliability, about design margins, and again, allows us to optimize product design.